Assalamualaikum and good day everyone. I will continue the lessons on punch transistor and transmission gates on asynchronous module. So today we will look at the difference between punch transistor and transmission gates. The punch transistor and transmission gates are introduced to help with a large scale integrations on chip. Therefore, to minimize the area, the pass transistor or transmission gates could be replaced the CMOS complementary cell. So, the difference between PTL pass transistor versus transmission gates is the number of the transistor. Meaning the number of instants. So in a previous class, I talked about and briefly explained regarding the NMOS pass transistor network. And there's some exercise at the end of the lectures. And today, I would like to highlight regarding the cascading pass transistor network. There's many types on cascading the pass transistor network. One of the methods is in series or in parallel. So, for this example, there's two instances of NMOS, M1 and M2. This is very similar with the exercise given at the end of the previous lecture. However, today we will look at the issue regarding cascading. Here is the layout. The P is defined as 2.5 volt or VDD. B is the control line or the control input to the gate. So this cell will be activated whenever this NMOS gate is on state. Here it's clearly seen that this NMOS is on state where B as a control input is set to VDD. Therefore, the Vs, I can call this Vs or I can call it X, is equal to VDD minus VT. These equations is obtained by understanding that VGS must be slightly larger or greater and equal to VT, and then VDS is defined as VGS minus VT. So for this example, VD is set to 2.5 volt, for example, at VDD. So I can call VDD is equal to 2.5 volt. Then the V gate also at 2.5 volt minus where VT here I claim as a 0.43 volt. So this example showing that the VD is larger than 2.07. Therefore, Vs is equal to X is equal to Vg Vt, where Vg is stated at 2.5 volt minus 0.43 volt is equal to 2.07 volt. And now we already obtained the voltage for this gate. So this gate voltage is examined to identify whether this is on state or off state. So our Vg is 2.07 volt and C is claimed as Vd 2.5 volt. So Vd is actually equal to Vg minus Vt, where Vt at the moment is 0.43 and Vg 2.07. So again, this Vt is leading the value. So it's greater than 2.07 minus Vt. So again, for these equations and this example, Vs or the Y is claimed as Vg minus Vt. So 2.07 minus Vt, or we can claim this as Vdd value minus Vtn1 minus Vtn2. So actually, this pass transistor should never be cascaded as on the left, because it will reduce, or the value of output voltage will be declined near the other half of the VDD. So on the right, there's a cascading system where it suffers from the static power dissipation. However, it reduces the noise margin. Okay, so when it reduces noise margin, you can see the noise margin low and noise margin high, and total noise margin is getting lesser, which means very small. So this is not a good switching system for a digital design. So for this example, whenever VDD, we check for this gate. X will be written as VDD minus VTN, and then Y is equal to VDD minus 2 VTN. The best cascading method is using this method. However, it suffers from the static power dissipation and reduce noise margin. So in order to avoid that problem, there's 3 solutions have been introduced to overcome the problem. First is a level restorer. This level restorer actually is to store this data of output X with a strong 1. So whenever this one is turned on, X is tied to 2.5 volt or VDD. You may refer to my video on a previous lecture regarding this information of level restorer. Therefore, this value of MR or transistor that being used as a level restorer must be sized correctly in order to make sure there's no static power consumptions by the inverter, and it's restore the data and sustain the output data nearly VDD. So another chance is by using solution number 2, multiple VT transistor. We can use a single transistor in order to provide low VT transistors. However, these methods is quite tricky because you have to understand the pass transistor on each path. So it also introduces time consumptions or more time to come up with the timing analysis. So the third solution is by using the transmission gates. This transmission gate is to provide strong 1 and strong 0, and to overcome the problem with weak 1 and weak 0. With post transistor logic, whenever NMOS is clear at 2.07, this is called as a weak 1. In order to avoid this problem, transmission gate is introduced. Let's test this example. Whenever A is VDD, C bar is equal to ground, so this PMOS is active, then C is equal to VDD, it will provide strong 1 because when the gate input for the PMOS at 0, it will provide strong 1. So this example will give you strong 1 instead of using NMOS pass transistor, we only provide us with a weak 1. So this is another example. When A is 0, VDD is set to the control line C, and this one is become 1. So this transistor ground is connected to PMOS, and VDD is connected to this control line C of NMOS. So for this example, it will give you strong 0 instead of provide a weak 0. So finish at the analysis on 3 times network, pass transistor logic, transmission gates with level restorer, single transistor, and also the transmission gate. Therefore, we can do the analysis on the transmission gate. Before we continue with the analysis on transmission gate, let me explain regarding the resistance of transmission gate. Similar with an instance of NMOS and PMOS, for PMOS, it has this equivalent resistance RP and also the equivalent resistance for the NMOS Rn. So from here, you can see that Rn is increasing and Rp is still decreasing. It's compensate each other. So the R equivalent will be in constant line. If both signs for NMOS and PMOS are given the same value. So transmission gate. Transmission gate can be used as a 2-to-1 multiplexer. First of all, let's draw the truth table of transmission gate. when B as a control line is stick to 0, then F is following the A. Then B is assigned at 1, F then is claimed as A bar. So using the pass transistor logic, with NMOS, you can claim that E B bar, and another one is A bar. We give with 2 transistors, is designed with 2 transistors. Actually, it's not 2 transistors. You must take note about this A bar and B bar. So in overall, this B bar is implementing by using the inverter B bar, and E and inverter A bar. So in overall, the total transistor is calculated as 6 transistors. However, this network of pass transistor logic suffers with weak 0 and weak 1. By redesigning the schematic of this network using the transmission gate, so it can help to reduce the problem with the weak 0 and weak 1. So for this transistor network, one transistor network can be claimed as one transmission gate. So we replace this network or this instance with transmission gate. So one instance now having 2 transistors. B is the control input. A bar is coming from one inverter from input A, then this one, this line, or this input is called as A bar. to the drain of the circuit. So let me wipe it a bit to avoid the confusions. Okay. How about this part? For the bottom line, for the top line. So now, when the input is A bar, B is turned on. If B is equal to 1, B is turned on, and A bar is permitted at the output. At the same time, B equal to 1 for the PMOS is given as B bar, and the gate value is become 0 due to the B bar. So again, this PMOS is also turned on. This provides a strong 0 instead of weak 1 due to a single pass transistor and MOS. And we want to solve this part by adding another transistor similar structure, transmission gate. In now is connected to this transmission gate, which is represent this network. Here is the B. This value actually tied together. Whenever B is 1, this NMOS is turned on for this network and also turned on for the other network. B is 1. However, when B is 0, B bar for the NMOS will turn on the NMOS transistor, meaning that the input is permitted at output. Here 0, so it's become 1. The input is coming from A. Then B bar, since B is equal to 0, it will turn on this PMOS. So at output, it's tied to F. This network of pass transistor logic of XOR functions or XOR cell is representing by using transmission gate by adding more transistors. So let's work out with the number of transistors. If we have B input, B that is tied to the inverter, and this network is tied to here and also tied to the upper network. So 2 transistors for the inverter, another 2 transistors for the inverter, adding with another 4 transistors for the transmission gates. Therefore, the number of transistors is increased into 8 transistors. Maybe the transmission gate solution suffer with the area consumption. However, it provides strong 1 and strong 0 logic for the output. this transmission gate is also claimed as or is claimed as a 2-to-1 multiplexer. In your exercise, I want you to design 4-to-1 multiplexer, and I will give the descriptions or the answers on 4-to-1 multiplexer and 8-to-1 multiplexer using the transmission gates and the pass transistor logic. So we continue with the differential or CPL complementary. This is also called as complementary TGL transmission gate logic. Last time we looked at the CPL for the pass transistor with MOS. Similar with the differential pass transistor logic, the differential transmission gate logic has a complement circuit for NMOS and PMOS. Let's test. In the previous solutions using the pass transistor logic of AND gate, we can claim that when the control line is 0, it's following the input A. When the control line is 1, it's following the E, and when the control line is 0, the output is tied to 0. So the pass transistor logic B is 0, B bar, is always tied to 0. And when the control line at 1, so all input of E is tied to the or permitted to the output. So now we want to represent this circuitry into a differential or complementary transmission gate logic. E, ground, B, ground for the AND gate. So E, first of all, look at E. E is tied to the B bar, and then it's tied to F. 0 ground is tied to B, which is NMOS, and then tied to 0. 1, then A input. Now A input, A input and B input. B input is tied, and it provides the bar for the A bar, for example in here, A bar, and tied to the output. And then the ground, okay, we have 2 ground, ground is tied with the NMOS to the output. Let's test this. We begin with this line. I list down all the input. A, B as A and B, 0, 0 as A bar, B bar. Since for the transmission gate, must have B and B bar. So again, I highlight A bar complement the A, and B bar for the PMOS complement the B of NMOS. So this line straight to the bottom. If the input is A, is 0, the control line is 0. The control line is 0. It's tied to B bar. B bar for the PMOS to provide a strong 0. Strong 1, and it's tied to the output. And then we have a ground input, meaning is 0. A represent the 1, okay, 1, 1. And 1 is 0, we have 1, 0 here. The ground, or 0, is tied to B bar. B bar. This is provide with 0, and then another ground. Sorry, there's a mistake there. To provide a strong 0 at the output, because we have input of 0 tied to the output. So it's provide a strong 0 by this NMOS. And another input called B is tied to A bar. It's tied to A bar. B is tied to A bar. To provide a strong 1. And the 0, another 0 here, is tied to provide a strong 0. This provide a strong 0. Here provide a strong 0. Here provide a strong 1. Here provide a strong 1. So A complement, then B bar and another sequence is called NMOS. This is providing one transmission gate. This is providing another transmission gate. So the single instance of NMOS is represented by a transmission gate B bar, and a single NMOS transistor is represented by the transmission gates in here. By using the differential logic system, is totally different compared with the CPL on post transistor logic, because you must take notes all the informations regarding the input, and not only using the one control line as the input, but using the input data to initiate or to design the pass transistor, the complementary transmission gate logic. So, I will give you another exercise regarding this differential transmission gate logic, and hopefully you will understand how to do it and can complete your exercise within 1 week. So since we are going to celebrate the Eid Mubarak, I will give a chance for the student to complete within 2 weeks. So after you coming back for the last class on interconnect, then I will provide the answer or the solutions on all given asynchronous classes. Okay, till then, thank you for watching and have a nice day.